and trying a bunch of practice problems. Maybe not that relaxing, but enjoyable. Okay, so let's take a look at some practice problems. This is from the 4th edition of Klein. It's question 7.75. The first question says we're starting with this secondary alkyl halide. We have a secondary alkyl. You could call it an alkyl chloride, so secondary alkyl halide. And we have a hindered base, a really hindered base, T-butoxide. T-butoxide is not going to be a nucleophile because it's so hindered. So we would say that this is a strong base, weak nucleophile. So you could write that in here. You could put strong base. I mean, technically it could be a good nucleophile, but it's just so hindered that it's never going to do that. So the only thing we're going to get are E2 reactions, E2 only. However, there's 3 types of beta protons we can pull off of this molecule. Let me just delete this for a second, and I'll show you what I mean. We have a beta proton here, and then here we have 2 types of beta protons because we can end up with 2 stereoisomers. We can end up with cis and trans stereoisomers when we make the Zaitsev alkene. Let me show you what I mean. Let's say if you ripped off the green proton, you could end up with the trans 2-butene, and if you ripped off the red proton, you'd end up with the cis-butene. Now again, we could end up with the 2 stereoisomers, which these are stereoisomers, but we could also end up with the regioisomer that comes from the abstraction of the blue proton. Now what my question is to you, if I'm using this bulky hindered base, could anybody tell me what the major product would be? Would it be the green, the red, or the blue? And again, there's no trick questions in organic chemistry. There might be difficult questions, but none that are designed to fool a student. Absolutely, it's going to be the blue one, isn't it? All right, why is it the blue? Because this is a hindered base. It's going to go for the least hindered proton, which is this blue one out here. Hindered bases, you could put here, give us the Hoffman product. And so this will be our major product. Okay, let's try another one. So this is B. We're starting with 1-chlorobutane, and we're treating that with sodium hydroxide. So we've got a strong nucleophile, strong base. So you could write that in here, strong nucleophile / strong base. And we have a primary alkyl halide. So what does that mean? It means that our predominant product, our major product, is going to be the SN2 product. Again, where did I get that? I looked at the table in our slides, and it's also present in our textbook, and it tells you that SN2 is going to predominate. So the hydroxide is just going to displace the chloride, right? We get our nucleophilic attack, loss of leaving group, and we end up with this alcohol. But we're also going to see some E2. Now, there's only one type of beta proton in here, and if this is our alpha carbon, this is the beta carbon. So you could draw the proton in here. That's not very pretty, is it? If I put the beta proton here, what's going to happen is you're going to abstract this proton, right? You're going to rip that off, form the pi bond, lose the leaving group, and that would give you 1-butene. So those are the 2 possible products, but the SN2 is going to be the major product, and we're being asked to identify the major product. Excuse me. Let's try another one that has a lot more products, or I guess more products. There's none of them that have thousands of products or anything. Don't get it out of hand here. So we're taking a compound that has a chiral center, the secondary alkyl halide, and we're treating it with sodium ethoxide. Now, sodium ethoxide is, again, a strong base, and it's a strong nucleophile. So what's going to predominate? E2 is going to predominate. But if I have an unhindered base, what's going to predominate? Could anybody tell me, would it be the Hoffman product or the Zaitsev product if I have an unhindered base? And again, it's not a trick question. What's going to predominate here? Exactly, it's going to be the Zaitsev product. Now hold the phone, because there's 2 Zaitsev products, aren't there? There's the trans 2-butene, and then there's the cis 2-butene. Now out of these 2 Zaitsev products, let me try to draw it a little prettier. Which one of these would predominate? Would it be the trans or the cis? They're both possible. Exactly. This one is going to be the major, the trans. Why? Because it's more, or it's less sterically hindered. So there's our major, but we're also going to end up with some of the Hofmann alkene. And if you look at that table, it tells you you're also going to get some SN2. Now remember that SN2 proceeds with inversion of configuration. So when my ethoxide attacks the electrophilic carbon, this one here, it's going to displace the bromine, but it's going to invert the stereocenter. So look, if I take my black pen and say my nucleophile is going to attack here, it's backside attack. And so that's going to give me 1, 2, 3, 4. But now my ethoxy group is going to be on a dash because of SN2 proceeds with inversion. Let me put here, inversion of configuration, like that. There we go. So we end up with 4 products in that specific case, 7.75C. Do I have to be able to identify them all? Yes. Do I have to know which one is the major one? Yes. This is part of organic chemistry. Let's move on to D. D, right? So let's see here. We've got a tertiary alkyl halide. Put the bromine over here like this, and we're treating it with sodium ethoxide. Sodium, a little better, sodium ethoxide. The sodium ethoxide is a strong base. It's a strong nucleophile. But I have a tertiary alkyl halide. Could anybody tell me what's the only kind of mechanism that's going to happen here? Would it be SN1, SN2, E1, or E2? Strong base, strong nucleophile, but a tertiary alkyl halide. What's the only thing that's going to happen here? The only type of mechanism? If you have to refer back to the table, if you're still practicing, go ahead. What's the only thing that's going to happen here? Would it be SN1, SN2, E1, or E2? If we go back to our table, so let's go back here. Find our table, which is down here somewhere, somewhere down here in the ether. No, that's not it. Keep going. Here it is. So this is the table I'm talking about. We have, here's my eraser. We've got we've got a tertiary alkyl halide. We've got a strong base, strong nucleophile. The only thing that's going to happen is E2, nothing but E2. So let's go back. The only thing that's going to happen here will be E2 reaction. So E2. Now, if I'm doing an elimination, and this is my alpha carbon, I have these methyl groups which have beta protons on them, but I also have this beta carbon as well. So if I pull off the blue proton, that's going to give me the Hofmann alkene like this. But if I pull off the green proton, then I end up with the Zaitsev alkene. If I'm using an unhindered base, like ethoxide, what's going to predominate will be the Zaitsev alkene. So this will be the major product, the one that I've written in green. There's no cis or trans to worry about here, so there's no stereoselectivity to worry about. Now, one question that students oftentimes will struggle with, or they find challenging at least, is ones that are stereospecific and stereoselective. So let's take a look at E, and we've already kind of looked at a couple that are stereoselective, 7.75. So in this one, we have a secondary alkyl halide. Remember that when you write pH like that, that means a phenyl. So that pH, it's the same thing as if I was to write out an aromatic ring like this. I just wanted to save a little bit of space. So now we're treating the secondary alkyl halide with sodium ethoxide in ethanol. So I've got a secondary alkyl halide, and I have a strong nucleophile, strong base. Could anybody tell me what mechanism is going to predominate in this case? SN1, SN2, E1, or E2? Secondary alkyl halide, strong nucleophile, strong base. What's going to predominate here? You have to go back to the table and look. Yes, thank you. It's going to be the E2 that predominates. We're going to get mostly E2. It's going to be the major with some SN2. So let's start with the E2. Well, if I look at the beta carbons, there's no protons attached to this beta carbon, so forget it. But this beta carbon has 2 protons attached to it. Therefore, the reaction is going to be stereoselective because we can end up with cis and trans products from the E2 reaction. Let's draw them both. So we'll start by drawing the trans, which would look like this. And then if we draw the cis, it's going to look like this. Which one of these would be the major product? Would it be the trans or the cis? Go with your gut. Could anybody tell me? Trans or cis? What would be the major product in this case? Yes, absolutely. This is going to be the major product. Why? Because it's less sterically hindered. So that we say the reaction is stereoselective for this product over the blue one, over the cis stereoisomer. Now, we can also get some SN2. What does the SN2 product look like? Well, we have a chiral center, and we know the SN2 is concerted. Nucleophilic attack, loss of leaving group occurs simultaneously, and so it occurs via inversion of configuration. Therefore, when we draw our ethoxy group, it's going to be on a dash instead of a wedge. And there you have it, my friends. We solved the entire thing. We figured out that there's 3 products, 2 stereoisomers, a cis and a trans. The trans would be the major. And then we also get some SN2 as a minor product as well. Let's try one that deals with stereospecificity. So this is kind of what I wanted to get into, because students will sometimes find these problems challenging, where we have stereospecificity or a stereospecific reaction, and this occurs where we have 2 chiral centers. Our alkyl halide is on a chiral center, and then our beta proton is at a chiral center. So the beta proton is coming out here like this. Again, on the aromatic ring, there's no beta proton, so the only beta proton that can be removed is this one. But what is the requirement for those protons? Can anybody tell me the word that we use to describe the arrangement of those, of the hydrogen and the bromine? What must they be in order for the E2 to occur when I treat this with sodium ethoxide? Because we know this is going to be the major product, will be elimination. Exactly. Thank you, Clinton. What he wrote is anti-periplanar. The bromine and the hydrogen must be anti-periplanar. So let's do this, Clinton. Let's move this out of the way first. Okay, and let's imagine that our human eyeball is looking down this carbon-carbon bond going from here to here. What would your eye see? Let's draw it. It's going to look something like this. So we're going to have the phenyl group going straight down. We've got the bromine going up and to the right. We have a hydrogen going up and to the left. And the carbon in the back, we've got the ethyl group going straight up. We've got the hydrogen on the right-hand side, and then we have our methyl group coming over here. So this is the hydrogen that I have circled in red, and this is the bromine. They are not anti-periplanar to each other. And so what I'm going to do is I'm going to move the hydrogen over this way. I'm going to rotate the bond counterclockwise by 120 degrees. So we'll put here counterclockwise 120 degrees. And when you do that, this is what you're going to end up with. So the phenyl's in the same place as it was. The bromine is in the same place. And this hydrogen. Now you've got your ethyl group over here. Your hydrogen is anti-periplanar to the bromine. And your methyl group is up here. So this is what you're eliminating. These 2 groups. So now when you do the E2 reaction, so I'll just write here E2, what you're going to end up with. So let me try to highlight it here. We'll start with this carbon. So let's say we have our double bond that looks like this. And this is the yellow carbon. You've got the phenyl on this side. You've got the hydrogen over here. But you can see that the ethyl group is on the same side. Please tell me that didn't delete it. Good. You can see that the ethyl group is on the same side as the phenyl. And so we've got our ethyl group coming off here, and we have the methyl group over here. And so this would be a Z compound. So this is the Z isomer, and this is going to be the major product. Let me write that in here, major product. However, we're also going to get some SN2 as well, right? E2, again, is the major, and there's only one E2 product, but we also get a little bit of SN2. I don't really have a lot of space to scribble it in. I'll write it down here, what the E2 product, or sorry, the SN2 product would look like would be this. So, oops, I can draw it prettier than that. 1, 2, 3, 4. Then I'm going to have my methyl group coming down here, and then my ethoxy group is going to be like that. So again, to rehash, this is our major product of the E2 elimination. This would be our minor product from SN2. Give me a thumbs up if you follow me on stereospecificity. Not easy. You have to employ a bunch of different things, don't you? Right, it feels good when you get it right, though, because you have to apply, first you have to understand SN2 and E2 reactions. You've got to understand which mechanism is going to predominate. You've got to understand if there's only one beta proton, it's going to be stereospecific if we have two chiral centers involved. You've got to understand Newman projections. You've got to understand how to manipulate a Newman projection, right? If there's one thing organic chemistry is, it's an additive subject, for lack of a better word. It's something where you really have to understand one chapter in order to proceed to the next one. It's very difficult to avoid a section of organic chemistry and just say, I'm not going to learn that part. I don't care about that part. Okay, and I know that none of you would do that. So let's try a couple more, and then we're going to have to move on to chapter 8. This is question 7.75. G, we could probably do this one pretty quickly. We have a tertiary alkyl halide, and we're treating it with potassium T-butoxide. What's going to predominate here? Could anybody just make a comment on what would predominate? SN1, SN2, E1, E2. It's not a trick question. What mechanism would predominate here? Yes, thank you. Great, thanks, Kiana. It's an E2, isn't it? Because we have a hindered base, it's not going to be a good nucleophile, and you've got a tertiary substrate. So you've got two types of beta protons. You've got the ones on the methyl group, and then you have the ones on these methylenes. If you pull the one off of the methyl group, then your alkene is going to be this compound. Whereas if you pull off the one in red, your alkene would be this. So this is our Zaitsev alkene. This is our Hoffman alkene. Could anybody tell me with T-butoxide, potassium T-butoxide, what's going to predominate? Which is the major? Would it be the Hoffman or the Zaitsev? Again, not a trick question. Yes, absolutely. It's going to be the Hoffman, isn't it? This is the major product because that base is just so gigantic. All right, let's do a couple more. Let's go a little quicker now just to kind of speed things along. H is in a similar vein to G. It's the same substrate, the same reactant, 3-bromo, 3-methylpentane, but now we're treating it with an unhindered base. And so now what's going to predominate is going to be, I missed a product, didn't I? Ooh, I just noticed that. Let me just move this out of the way. Oops, Mr. Dion, I didn't make a mistake. I just noticed that I missed a product, didn't I? Because this is the cis isomer over here. This is the cis. And then there's also a trans, isn't there? So if you write this, so there's also this isomer, which is a trans. But that's also a minor isomer. I just noticed that. My mistake. Okay, so for the next one, same thing. I'll just, maybe I'll just copy and paste everything because it's the exact same possible product, for the next question. So if I copy this, let's see if it'll work. Nope. Okay, so let me redraw them all. I can have the Hoffman product. I can have the cis Zaitsev product, and I can also have the trans Zaitsev product. So I have it like this. Could anybody tell me which would be the major product here? Would it be the blue, the red, or the black in this case? If I have an unhindered base like sodium methoxide. In this case, this one is going to be the major product. This one here would be the major product, okay? Even though it's cis, it's less hindered. This one would be the less hindered because it is the E product. Okay, this is the largest group. This is the largest group on those sides. And so that would be the major product here. Let's try another one. Let's try I, and then maybe we'll have to move on. Chapter 8. So this is question 7.75. I, we're starting out with a chiral center in our molecule. This here, we're treating it with sodium hydroxide. And what are the possibilities? We've got a strong nucleophile, strong base. E2 is going to predominate, and we're also going to get some SN2. So there's 3 possible E2 products. We could get the Hoffman product if we pulled off this proton. If we pulled off one of these protons, we can get the trans Zaitsev product. If we pull off another one of these beta protons, we can get the cis Zaitsev product, and then we can also get the SN2 product, which is going to occur, the reaction occurs by an inversion of configuration, and so we get this alcohol. The major product is going to be the Zaitsev product, and it's going to be the least hindered one. So this would be our major product. If we take a look at 7.75I, so I'm sorry, J, that's this one here where we have a hydroxyl here, and we're treating this with concentrated sulfuric acid, and we're just cooking it up. What's going to happen here is you're going to convert the alcohol into a good leaving group, right? We convert that into a good leaving group, and then we can have several eliminations occurring here, can't we? We can form the Hoffman product, we can form the Zaitsev product, but remember this leaving group is going to leave, and when it leaves, we end up with a secondary carbocation like this, which can undergo a hydride shift. So let's draw that to give us, oops, I can draw that a little better, to give us a tertiary carbocation, which can then undergo an elimination to give us another Hoffman alkene like this. So we could end up with all 3 of these, but remember, the major product is going to be the most substituted one, and so this Zaitsev product would be the major product of this reaction. Let's look at the last one. So this is 7.75K. We're starting off with a compound. We've got a tosylate, which is a good leaving group. We've got a chiral center. So remember, tosylate is good leaving group. And we're treating it with sodium chloride and DMSO. Remember that DMSO was a polar aprotic solvent. We've got a secondary alkyl halide, and we've got a good leaving group. And remember that chloride is a strong nucleophile, but it's a weak base. So we're not going to get any elimination here. We're only going to get SN2. And that's the only thing that we're going to see is inversion of configuration, and we replace the tosylate for a chloride. So SN2 only in this specific case.